Welcome to our next video on periodic trends, which is going to be looking at energy trends. So in this video here, we're going to take a similar approach to what we did with the size video, and we are going to describe or define ionization energy and electron affinity. And for both of those, we are going to explain the periodic trends, and we'll go through an example of each to show how we explain it in terms of atomic structure. So to start with, let's talk about ionization energy. The simple definition is it just refers to the amount of energy required to remove an electron from an atom or an ion. So even though we see the word ion there, and an ion can be an atom which has gained or lost an electron, when we talk about ionizing something and ionization energy, it's always talking about in the context of removing an electron. We'll be writing it so much that we can always just short form it to IE. And IE is a measurable quantity. What does that mean? That means that there is some sort of numerical measurement assigned to it, okay? And it's just an energy. So you might see it in electron volts, or you might see it in kilojoules, some energy value. So what do these values mean? The greater the ionization energy value, so that numerical quantity, the more energy is required to remove an electron. Another way of looking at it is the higher the ionization energy, the stronger the nucleus's hold is on the electrons. One thing that we will look at is successive or multiple ionization energies. And we'll just note right now that if you're trying to remove the first electron, so going from an atom to a 1+ ion, that's referred to as IE1, one electron. That amount of energy is always less than trying to remove the second electron. So IE2 is going from a 1+ ion to a 2+ ion. And then that's going to be less than the energy required to remove the third electron. So every time you try to remove another electron, so you're making the ion more and more positively charged, it takes more and more energy to do that. So let's take a look at what the periodic trend is in ionization energy. If we are within a period moving to the right, ionization energy increases. And within a group moving down, it decreases. So what's that telling us? Within a period, the electrons are held more and more strongly as we move to the right. And as we move down, those valence electrons are held on less strongly as we move down within a group. So let's now take a look at an example. So here's our example. Rank the following elements from lowest to highest ionization energy: beryllium, oxygen, sulfur. So we're going to switch over to the whiteboard right now and go through that example together. So for our example here, we are looking to rank these three elements in terms of their ionization energy. Just like we did with the size trends, let's start off by calculating the core charge for each of these three elements. Might be good practice right now. Pause the video and calculate the core charge. And while you're doing that, compare each of these in terms of their electron shielding as well. So take a pause right now and come back and you can check your answers. Okay, so for beryllium here, we have a core charge of 4 protons, subtract 2 inner electrons, core charge of 2. Oxygen, 8 protons, 2 inner electrons, a core charge of 6. And for sulfur, 16 protons, subtract 10 inner electrons, a core charge of 6 as well. Let's compare the force of repulsion now. Repulsion is due to complete inner shells of electrons, the electron shielding effect, and we can see right here, sulfur has 2 inner shells of electrons. Beryllium and oxygen both have 1 inner shell, so that means sulfur differs from them in terms of the force of repulsion. So now what we want to do is rank these in terms of their ionization energy. So ionization energy, the energy required to remove an electron. The stronger the force of attraction and the weaker the force of repulsion will increase the ionization energy. The more tightly those electrons are held on, the more energy it's going to take to remove one. So sulfur is not going to have the highest ionization energy because it has that extra shell. So we find that there's larger changes between periods than there are within a group. So that's why I'm looking at the force of repulsion to start with. So I'm going to eliminate sulfur and just say for right now it's going to be the lowest. So maybe I'll start off by ranking these down here and say sulfur is going to be less than. Now I'll compare my next two. Beryllium and oxygen, same force of repulsion, but beryllium has a lower core charge, which means those 2 valence electrons are held on less tightly. So it will take less energy to remove beryllium's electrons. And finally, that means oxygen will have the highest ionization energy. So once again, calculate core charge, compare shielding, and then I start off by looking at the force of repulsion first, and I put sulfur down there with the lowest because it has the most repulsion, and then I compared within the second period. So now that we've talked about and drawn our answer, let's more formally write down an answer for this. Once again, my Bohr-Rutherford diagrams and core charge calculations are the justification or the evidence that you need to show me that to back up the answers you're giving me here. Okay, so you can't just say sulfur has the most repulsion. Okay, you showed me that using your Bohr-Rutherford diagram. So first of all, we saw that sulfur had the most repulsion, and I said the changes between periods are always greater. So we'll use repulsion first and rank that one as the lowest ionization energy. And then we will compare within a period. Beryllium and oxygen. Oxygen has the highest core charge, strongest force of attraction. Therefore, it will have the highest ionization energy. And so beryllium's the only one left, and it's going to go in the middle. So I clearly rank it. Sulfur, less than beryllium, less than oxygen. Okay, so let's move on to our second trend here, which is going to be electron affinity. So one of the most difficult things about periodic trends in energy is the confusion which results in thinking about ionization energy and electron affinity. Because some things are going to be the same about them, even though they're talking about opposing processes. So remember, ionization energy was energy that was having to be put in to remove an electron. Electron affinity is looking at it from the other perspective. How much energy is released when an atom gains an electron? Now, why is energy released? Well, this is something that we're going to see throughout this course, is that when an attraction is formed, whether it's a chemical bond or whether it's an attraction between a nucleus and an electron, energy is released when there's a new attraction formed, and the stronger the attraction, more energy is going to be released. So when it comes to electron affinity, The more positive the energy value indicates that more energy is released, which tells us that there's a stronger nuclear attraction. And you'll see the word attraction come up a lot with electron affinity, and that's a good way to remember that, is electron affinity is talking about electron attraction. The stronger the nuclear attraction, the stronger or the higher the electron affinity. Okay, let's now look at the two trends. Moving to the right in the period, across the periodic table, the electron affinity increases. Atoms progressively get stronger and stronger electron affinities. Moving down within a group, the electron affinity decreases. Their values get smaller and smaller as you move down. So let's now take a look at an example. Identify the element with the lowest electron affinity and justify your response. So before we get into the example, let's just think about what that means. Low electron affinity is going to be a small energy value. A small energy value indicates a weaker attraction. So when we're comparing these elements, we're going to be looking for high repulsion and low attraction. So let's switch over to the whiteboard right now and take a look at this example. Okay, so here's our example for comparing electron affinity. And so we were asked to find the element with the lowest electron affinity. So as we've done in previous examples, let's start off by calculating the core charge and comparing the electron shielding effect. And then we'll apply it to the question. So once again, practice right now, pause the video, and try to make those calculations yourself. So for sodium, its core charge is 11, subtract 10 for its inner electrons, core charge of 1. Aluminum, 13 protons, 10 inner electrons, core charge of 3. And fluorine, 9 protons, subtract 2 inner electrons for a core charge of 7. And then if we compare the shielding effect, we see that there's more shielding between sodium and aluminum. And so fluorine here is the one that differs in terms of shielding. So we could say that fluorine has a lower force of repulsion than the other. So I'll just highlight the difference. So we want to find the element with the lowest electron affinity. So remember, electron affinity is talking about electron attraction, the amount of energy released when an element gains an electron. The stronger the force of attraction, the weaker the force of repulsion, those factors there will result in a stronger electron affinity. So what we are looking for is elements with lower forces of attraction and higher forces of repulsion. So immediately here, we know we can eliminate fluorine, okay? So I'll just put an X there because fluorine has a high force of attraction and a low force of repulsion. Now I'm going to compare sodium and aluminum. They have the same force of repulsion, so no difference there. But sodium has the lowest force of attraction. So that means sodium we would expect to release the least amount of energy or have the lowest electron affinity. Now that we've gone through the example, let's just formally put down the answer. So we first started off by eliminating fluorine because it had the opposite forces that we were looking for. So fluorine had a high core charge, strong attraction, and low shielding, which meant it would have a high electron affinity. Makes sense, right? We know that fluorine is very reactive and reacts by gaining electrons. So now we compare sodium and aluminum, and we saw that they both have the same amount of shielding, so no difference in the repulsion, but sodium has the lowest core charge, meaning it has the lowest force of attraction, so it will have the lowest or smallest electron affinity.